Hello everyone. So today's session we will discuss about instrumentation amplifier. So in many industrial and consumer applications, the measurement and control of physical conditions are very important. For example, measurement of temperature inside a dairy farm. It will permit the operator to make necessary adjustments to maintain the product quality. Similarly, precise temperature control of a plastic furnace is needed to produce a particular type of plastic. So, for this we generally use a transducer. So, transducer is used to at the measuring site to obtain the required information easily and safely. So, the transducer is a device that converts one form of energy into another. So, in this block diagram you can see a instrumentation system in which you will see the first block is the input stage that will consist of a transducer or a preamplifier, and the next one is the intermediate stage which is we call it as the instrumentation amplifier, and the output stage that we use generally an indicator or a automatic process controller. So all these stages are connected with the transmission lines. So you can see that first of all we give some input, that is which quantity, physical quantity you have to be measured, that will give to the input stage where the transducer will act as the will convert that input physical quantity to another energy format that will pass into the intermediate stage, that is the instrumentation amplifier system, and then where it will be convert into the some voltage or current that we can measure in the output stage, or we can see that using some indicator, voltmeter, ammeter, that we can give into the output stage. Okay, so this is the general block diagram of an instrumentation system. So block diagram of an instrumentation system. So usually transducer is the main type of transducer is thermistor, photo cells. We generally use the thermistor where the physical quantity that we measure is the temperature. So as temperature increases, there will be changes in the resistor. So thermistor usually temperature increases, resistance decreases, negative temperature of coefficient. Okay, and another thing is photo cells, where the light falls, the intensity will affect the resistance of the circuit. So photo cells. Then another one is strain gauges. So strain gauge usually we give some physical or mechanical energy, some forces to the that particular input stage, then it will convert into the electrical, that is resistance itself, electrical energy likewise. Okay, so these are the main type of transducer we use in our lab. We did this experiment, instrumentation amplifier, using transducer, where we use the thermistor as our transducer. Okay, so in the next figure you can see that this one is the first part. You can see this portion is an balanced bridge, you can see here, and two op-amp is given here in which we will give the voltage of balance voltage to the this amplifier. So VA to first A1 amplifier and VB to the second amplifier. So the differential voltage will given to the another amplifier and it will give the output. The output will give to the indicating meter. These are the simplest form of an instrumentation amplifier using a transducer bridge. So instrumentation amplifier using a transducer bridge. So here you can see this portion is the transducer bit. Where the four resistance are given: RA, RB, RC and RT. The RT is the actually is the transducer resistant or resistive transducer that we can usually call. Usually we will give here thermistor, photocells like components. So this usually we know the bridge is balanced when VA equal to VB. That is the main condition here. So the reference condition will be VA equal to VB, that both voltage will be same when the bridge is balanced. Okay, so for this we mainly consider two circuits and just make this as exactly half portions. Okay, so we can consider this loop and we can consider this loop too. Totally two loops. From here we can get VA, the voltage from this portion, and the next portion will be this, like this. Okay, so VB is the another voltage coming from the two loop. So the bridge is balanced only when it satisfies the reference condition. Balancing condition will be condition VA equal to VB. That is the balancing reference condition. Okay, so now we will consider what will be VA equal to. So VA equal to, that we can write it from here, VA. So this voltage VDC is given to RT plus or minus delta R. Now we just consider only RT. Okay, so this portion I am just avoiding it. Okay, only consider RT only, the thermistor or transducer resistance only. Okay, so VDC is passed through the resistance RT and RA and reaches to VDC itself. This is the one loop. Okay, so VA will be equal to RA into VDC divided by RA into VDC divided by RA plus RT. That is the equation for VA. Next we consider the other side of the loop. Then we will get VB. VB will be equal to RB VDC divided by RB plus RC. So this is the equation for VB. Then we can equate for the reference condition, bridge balance, VA will be equal to VB. Then we can write it as VA equal to VB, and then we can write VB equal to VA, anything. Then we can write RA VDC divided by RA plus RT, which will be equal to RB VDC divided by RB plus C RC. Okay, so this is the general equation, and we can write it as VDC will cancel, and we can write it as RC by RB equal to RT by RA. So this is the general equation. This is equation number 1 and equation number 2, and this is equation number 3. So generally resistors RA, RB and RC are selected so that they are equal in value to the transducer resistance RT at some reference condition. So we can generally take it as RA, RB, RC will be equal to RT at some reference condition. So the reference condition is specific value of physical quantity and the measurement at which the bridge is balanced. So we can write, we can tell that the bridge is balanced initially at a desired reference condition. However, as the physical quantity to be measured changes, the resistance of the transducer also changes, which causes the bridge to unbalance. So bridge is balanced only for the reference condition. As if there is some changes in transducer resistance, this balancing will be unbalanced. Okay, so which causes the bridge to be unbalanced. So in that condition, we can say that there will be some changes in resistance. That's why in the figure we written it as RT plus or minus delta R. So there is some change in transducer resistance. Okay, so when the bridge is unbalanced, VA not equal to VB, then we can write it as there will be some changes in transducer. So some changes in transducer resistance, that is RT plus or minus delta R. Okay, so since RB and RC are fixed resistors, the voltage VB is constant. So RC, RB we can make it as a fixed resistance, so VB is constant. However, voltage VA varies as a function of change in the transducer's resistance. So RT changes, that means VA will change accordingly to the transducer resistance. So we can write this equation as, from this one we can write it as VA equal to RA VDC divided by RA plus RT plus or minus delta R. This is the main equation of VA for some changes in the transducer resistance. And we can write VB equal to RB VDC, that is the main equation, and RB plus RC. Okay. So consequently we can see that the main voltages VA and VB coming to the differential amplifier, that is the instrumentation amplifier system. There is a differential voltage coming to the entire amplifier system. So we can write the voltage VAB will be equivalent to VAB, which is the change in voltage VA minus VB will be equal to RA VDC divided by RA plus RT plus or minus delta R minus RB VDC divided by RB plus RC. So this is equation number 4. So when RA, RB, RC, RT equal to R, RA, RB, RC RT equal to R, then we can write VAB will be, then equation 4, VAB equal to delta R VDC divided by 2 into 2R plus delta R. Okay, here 2R plus or minus delta R, that's okay. So 2 into 2R plus or minus delta R. So this is equation number 5. So now we got the differential voltage that we applied to the op amps. Now we have to find out what will be the output voltage of the circuit. So the output voltage of the circuit V0 will be, that you can see here, V0, that we can the output voltage circuit, output voltage of the circuit V0 equal to VAB into, that is the differential voltage, VAB into minus RF by R1. So here VAB into the gain of the circuit, differential amplifier circuit gain will be minus RF by R1. So V0 equal to VAB into minus RF by R1. So just equate the equation 5 into this equation. Then we can write V0 will be equal to delta R VDC divided by 2 into 2R plus delta R RF by R1. Okay, so this is the equation. So here you can write the equation VAB will be equal to the sign with the negative sign. Okay, so we can write V because VA should be less than VB. So in that condition we can write the VAB will be equal to minus delta R VDC 2 into 2R plus delta R. So when we consider the output voltage VAB, this minus and minus will be cancelled. So we can write the equation as delta R VDC by 2R plus delta R RF by R1. So I will just write the condition here. We can put negative sign in this equation so that it indicates that VA is less than VB. Why? Because in VA we have the transducer resistance, so there will be changes in that resistance. So VA should always less than VB. Okay, so we can write this VAB as with the negative sign. Okay, so on these both negative signs will come. We can write V0 will have delta R VDC 2 into 2R plus delta R into RF by R1. So generally we can say this term 2R plus delta R is approximately equal to 2R itself. So we can write V0 equal to RF by R1 delta R by 4R VDC. So this is the final equation. So this one fifth and this one sixth. Okay, so this is the final equation in that indicates that V0 is directly proportional to the change in the transducer resistance delta R. Okay, so we can generally indicate that voltage in that circuit using some changes in the transducer resistance. We can indicate that changes in the indicating meter, or we can use some voltage voltmeter or ammeter, any equipment. So we can see that the changes will changes here. Okay. So now we discuss about the two applications that we used in transducer. So that one of the application is temperature indicator. Temperature indicator. So in dairy farms, usually we have to maintain particular temperature in the dairy products. Okay. So if usually we give some transducer in inside that dairy product or that storage places, we place some transducer. Okay. So if there is any changes occur, and usually we maintain some reference conditions there, that the dairy product will be better in that temperature, usually the cold temperature. Okay. So if there is any changes, this transducer accept that change, and it will pass through the transmission lines and will get to the instrumentation amplifier, and we are only indicating meter with us. Okay. So we will generally note on the changes in that output equipment. So we can understood that if there is any changes in the temperature. Okay. So usually we use instrumentation amplifier as a temperature indicator. So only the change here you can see is the resistive transducer. We can use some thermistor or photo cells there or anything. So mainly in temperature cases we give the thermistor as the transducer, and the output we give some voltmeter, something for realizing that changes. Okay. The second application will be light intensity meter. So light intensity meter. So in this case, for instead of thermistor, we use photo cells. So in this place, we generally use a photo cell as the light intensity meter. So the bridge can be balanced for darkness condition. Therefore, when exposed to light, what will happen? The bridge will unbalanced and cause the meter to deflect according to the resistance. So as the intensity increases, the resistance will decreases. So we can see that there are some changes in the indicating meter. So we can correspondingly plot the graph or take down the values. We can understand that there will be changes in the transducer bridge. Okay, so these two are the applications for temperature indicator and light intensity meter. Now we do one problem based on the temperature indicator session. So in this the circuit, the values for the all RA, RB, RC and RT are given. So we can find out the output voltage at 0 degrees Celsius and at 100 degrees Celsius. So I will just write down the values of RA and RB here. Okay, so problem. R1 equal to 1 kilo ohm, RF equal to 4.7 kilo ohm, RA, RB, RC equal to 100 kilo ohm. VDC is given, which will be equal to plus 5 volt, and op-amp supply voltages is that usually we use 15 volt. So op-amp supply voltage of op-amp supply voltage equal to plus or minus 15 volt. So here we use the transducer as thermistor. So the specification for thermistor specifications will be RT equal to 100 kilo ohm at reference temperature of 20 degrees Celsius. At reference temperature of 20 degrees Celsius. Sorry, 25 degrees Celsius. And the temperature coefficient of resistance is equal to minus 1 kilo ohm per degree Celsius. Then we have to find the voltage at 0 degree Celsius and at 100 degrees Celsius. Okay, so first of all, we 0 degree Celsius, delta R is the resistance of the thermistor. So in that condition, we will find out the delta R of the circuit. So that the equation that we used for find out the delta R will be temperature coefficient of the resistance, temperature coefficient of resistance into final temperature minus initial temperature. So this is the equation for delta R. So that we can apply here and we will get temperature coefficient of resistance will be minus 1 kilo ohm by degree Celsius, and final temperature and initial temperature will be so minus 1 kilo ohm by degree Celsius. Final temperature here is 25 degrees Celsius, and at a reference temperature will be 25 degrees Celsius. So this one will be the final temperature. So we can write it as 0 degrees Celsius minus 25 degrees Celsius. Okay, so in the case this one will be equal to 25 kilo ohm. So that will be the delta R, and we can use the equation sixth equation for finding out the value of V0 at 0 degrees Celsius. So here we have to find the V0. Determine the value of V0, the output voltage at 0 degrees Celsius and 100 degrees Celsius. So V0 at 0 degrees Celsius equal to, that is V0 equal to the value we have put it here, RF by R1 delta R by 4 into VDC. That is the equation that we are going to apply here. So V0 for RF by R1 delta R by 4R VDC. So we can apply the values for VRF, that is 4.7 into 10 raised to 3 kilo ohm. So and R1 is 1 kilo ohm, 1 into 10 raised to 3. Delta R is, that we already find it, 25. Okay, 25 into 10 raised to 3 divided by 4R. 4 into R will be, that is 100 kilo ohm. So 4 into 100 into 10 raised to 3. VDC will be 5 volt. Okay, so from this we can find out the value for V0, that is equal to 1.47 volt and now we will find out V0 at 100 degrees Celsius. So V0 at 100 degrees Celsius, apply the values here, and we find out that for this case the delta R will be minus 1K degrees Celsius, 100 degrees Celsius, that is the final temperature, minus 25 degrees Celsius, and we will get the delta R for the 100 degrees Celsius range. It will be 75 kilo ohm, minus 75 kilo ohm, and we can find out the V0, which will be equal to 4.7 into 10 to the power 3, 1 into 10 to the power 3, and 75. These are the delta R. Minus 75 into 10 to the power 3 divided by 4 into 100 into 10 to the power 3 into 5, and we will get the value as minus 4.41 volt. So the output voltage will be vary from 1.47 volt to minus 4.41 volt. This one will be corresponding to 0 degrees Celsius, and this one will correspond to 100 degrees Celsius. So these are the voltmeter ranges that shown in the indicating meter, from 1.47 volt to minus 4.47 volt. Okay, thank you. So hope you understood. Thank you.